Here we're going to use Kepler's third law to measure the mass of the sun. And the way this works is if you have a planet going around a star, and you know its distance from the star, and you know the time it takes, you can use that to get the mass of the star right here. So we need to first convert 365 days into seconds. And if we do that, that's going to be 365.25 days. There's 24 hours in a day, and there's 3,600 seconds in an hour. So that when we evaluate that, we will end up getting quite a big number, actually. Let's work that out. So 365.25 times 24 times 3,600 gives us 3.16 times 10 to the 7th seconds. Given that, we can now get the mass of the sun. So 150 times 10 to the 9th, and we will cube that, divided by 3.17 times 10 to the 7th squared equals g, which is 6.67 times 10 to the negative 11th, mass of the sun divided by 4 pi squared. Continuing to simplify, 4 pi squared, 150 times 10 to the 9th cubed, divided by 3.17 times 10 to the 7th squared. Don't forget to divide by 6.67 times 10 to the negative 11th. And then we'll isolate the mass of the sun here. And when we actually work that out, we're going to end up getting 2.0 times 10 to the 30th kilograms. For anybody who's interested, that means we're a little under a million times the mass of the Earth. So, a planet outside our solar system has a moon that orbits it with a period of 50 days and has a distance of 700 times 10 to the 6th meters. We want the mass of the planet. Once again, we need to convert days into seconds. So 50 days times 24 times 3,600 gives us a time of 1.728 times 10 to the 6th seconds. That's the time. And now we're going to go ahead and get the mass of the planet. So I'm going to actually do this with algebra first. So r cubed over t squared equals g times mass of the planet that we find divided by 4 pi r squared. Isolating, we're going to get the mass of the planet in question is going to be 4 pi squared r cubed over g times t squared. Simplifying here, we are going to get as our answer, when we simplify, let's actually put in our numbers first. So that's 4 pi squared. R cubed is going to be 700 times 10 to the 6th. And we'll cube that. We'll divide that by 6.67 times 10 to the negative 11th. And we'll also put t squared in there, which is going to be 1.728 times 10 to the 6th quantity squared. When we simplify that out, we will end up getting 2.16 times 10 to the 25th, which is about a little under 4 times the mass of Earth, by the way. So it says if the planet question item has the following radius, we want to know its gravity at the surface. So let's go ahead and calculate that out. So G is going to equal capital G, mass of the planet, divided by radius of the planet squared. It's going to be 6.67 times 10 to the negative 11th times 2.16 times 10 to the 25th. And we're going to divide that by the radius of the planet squared, which is 3 times 10 to the 6th squared. When we go ahead and solve for the gravity, I'm getting a gravity of 160 meters per second squared, which is actually 16 times Earth's gravity. So most likely, no. Probably not going to be supporting gravity on a planet like that, supporting life on a planet like that. Next, we say a star orbits a planet at a given distance and has a period. And we actually want to get the mass of the star that it orbits. So let's go ahead and do that now. So 25 AUs in meters. I'm going to actually use Google for that. So we will say 25 AU in meters. So that's getting me 3.74 times 10 to the 12th. All right. And the period of 30 years, let's get that in seconds. So that's 9.5 times 10 to the 8th. I'll round a little bit. So 9.5 times 10 to the 8th. Let me just double check that. Indeed it is. Times 10 to the 8th seconds. Now, I'm going to use this formula here that I got for the mass. I think isolated, that'll be 4 pi squared r cubed over gt squared. That'll be 4 pi squared, 4 pi squared, 3.74 times 10 to the 12th cubed over 6.67 times 10 to the negative 11th, and it's t squared, so 9.5 times 10 to the 8th, and we'll square that. So the mass of this star, let's go ahead and get it now. And our mass of this star ends up being 3.4 times 10 to the 31st. By the way, when we compare this to the mass of the sun, this is going to be about 170 suns. Let me just double check that though. So 3.4 times 10 to the 31st divided by 2 times 10 to the 30th gives us 68 suns worth of mass. Let me make absolutely sure I have that right. So the mass of the star divided by the mass of the sun equals 3.4 times 10 to the 31st divided by 2 times 10 to the 30th, which gives us about 17 suns worth of mass. I think at this size, a star this big, I'm pretty sure it collapses into a black hole when it dies. So we'll have to be clear on that. All right. Now here, this little force question we're going to take a look at the next time in class. So we'll hold off here and I'll publish this to PowerSchool right now.